In this video, we're going to talk about graded potentials and action potentials. So first, let's look at graded potentials. Graded potentials occur essentially in the dendrites and the somas of a neuron. So here we can see that we have mechanically gated sodium channels in the dendrites, and we have ligand or chemically gated sodium channels here on the main soma. So let's first direct our attention towards the mechanically gated sodium channels. So on a mechanically gated sodium channel, they're basically opened by touch. So if we stimulate the cell by touching it, what that'll do is temporarily open this channel, and that will allow sodium ions from the extracellular fluid space out here to now enter into the cell. Now we know that first the cell starts off with a resting membrane potential of negative 70 millivolts, negative there, and for it to get excited and to create an action potential, we must reach negative 60 millivolts. So a graded potential is the positive movement from the resting membrane potential towards the threshold potential. The neat thing about these graded potentials is that they can be weak or strong, and they're also decremental, meaning that they get weaker over time. Okay, so let's pretend that we stimulate this cell by touching it only momentarily, and that allows, say, 3 sodium ions in, which would change our resting membrane potential from negative 70 to about negative 67 millivolts. If we go over here and look at the graph, it would basically go from a negative 70 millivolt charge, which is resting membrane potential, to slightly above that. We would call this an excitatory postsynaptic potential. Basically, anything that makes the cell more positive is an excitatory postsynaptic potential, and this can be created by a stimulus such as touch. It can also be stimulated by a chemical. For instance, acetylcholine is a chemical that can bind to acetylcholine receptors on the surface of the soma. They can also let sodium in, and they can do the same thing. Maybe only enough acetylcholine binds to where 3 sodiums get in, changing the resting membrane potential from negative 70 to negative 67, and it can create the exact same type of excitatory postsynaptic potential. So there are basically 2 routes to create this graded potential, either mechanically through stimulation or chemically. Okay, in this case, neither door stayed open long enough to reach threshold, and so that graded potential basically died off and resulted in no excitement of the cell. Okay, now for an action potential to be created, we're going to have to reach threshold. So we would need a very strong, graded potential can result in an action potential. So as long as there is enough acetylcholine bound to acetylcholine receptors, or if the mechanical touch is strong enough to keep these doors open, once enough sodium has come in to basically increase the charge the entire stretch from negative 70 to negative 60, which is a 10 millivolt charge, that will then result in an action potential occurring. So once we reach threshold, an action potential occurs, and as we said earlier, the formation of an action potential here at the axon hillock will open up voltage-gated sodium channels. Once that happens, lots and lots and lots of sodium will be able to flood into the cell, and that leads to a very strong increase in charge. This whole process is known as depolarization. Basically, the depolarization consists of sodium flowing into a cell and creating the action potential. So a depolarization is the creation of an action potential. Okay, next I'd like to talk a little bit more about graded potentials. Graded potentials come in 2 variations. There are excitatory postsynaptic potentials, which basically are anything that makes the cell more positive. As we just saw, to make the cell more positive, sodium flows into the cell, and that then makes the cell more excitable. Basically, it is closer to threshold. So any EPSP will basically look like this. It's an upward movement on this graph. On the other hand, there are also IPSPs, which stand for inhibitory postsynaptic potentials. These are anything that will make the cell more negative. This typically involves the movement of potassium, not sodium, out of the cell. So we know that potassium is typically found in the intracellular space, and so if potassium is allowed to pass through a separate door or a separate channel, then that potassium will leave the cell and take its positive charge with it. So every time a potassium leaves, that actually makes a negative direction move on our little graph here. So as potassium leaves and takes its positive charge with it, the overall charge of the cell becomes more and more negative. All right, this will make the cell less excitable, farther from threshold, and so will be harder to stimulate into excitation. Okay, so the next thing we're going to talk about is an action potential on the graph from start to beginning and which channels are open and close. So as we said earlier, it all begins with sodium entering into the cell. So as soon as sodium begins to enter the cell, typically due to the opening of a chemically gated sodium channel, like an acetylcholine gated sodium channel, this results in a positive uptick on our graph here. Okay, at that point, an action potential is created. And so once enough sodium has come in to hit threshold, that creates our action potential. And that basically opens up voltage-gated sodium channels, allowing sodium to enter into the cell at a very fast, rapid speed. So this is sodium in, and we would call this the depolarization process. Now at this point, the cell is very positive and, believe it or not, unhappy. So for the cell to get back to its resting membrane potential of -70, we're going to have to get rid of a lot of that positive charge. And the easiest way for the cell to do it is to allow potassium to exit. So potassium is typically an intracellular ion, and it has got a voltage-gated potassium channel on the surface as well. So once we hit this very positive charge, that's going to be the impetus for opening these voltage-gated potassium channels. And once they're opened, potassium is going to leave. And as potassium leaves, it's going to take its positive charge with it. So the more potassium leaves the cell, the more negative our overall charge becomes. Now the interesting thing is that potassium is repelled by sodium because they both have the same charge. And potassium is so repelled by sodium that more potassium will actually leave than needed to get the charge back to its resting membrane potential. At this point, we've become extra negative. And the term we use for this is to be hyperpolarized. Okay, and I missed it here. When the potassium levels first opened, we'd say that potassium is going to leave the cell, and this process is known as repolarization. Okay, so the initial steps would be, once again, for the ligand-gated or mechanically gated cells channels to open in the cell, allowing sodium to slowly enter in. If we reach threshold, then that will open up voltage-gated sodium channels, allowing sodium to flood in at a rapid pace, creating depolarization and an action potential. At that point, once we've reached a very positive charge, that will open up a second type of gate called a voltage-gated potassium channel. Once these channels open, potassium is allowed to leave, and as it leaves, it takes its positive charge with it, resulting in a negative charge. So much of the potassium leaves that the cell actually becomes extra negative for a time being, where we call it hyperpolarized. It'll eventually get back to its normal position. And this will involve getting sodium back out of the cell, getting potassium back into the cell, which uses our sodium-potassium pumps. Sodium-potassium pumps will pump 3 sodiums out for every 2 potassiums in, and it'll do this until the cell is returned to its completely natural state with intracellular potassium and extracellular sodium.